Welcome to the second part of topic 3. At this point, we've spent 3 days on implicit differentiation, so hopefully you're feeling pretty comfortable with that. We're actually going to use it one more time today and then a bunch in related rates, so you won't forget it and you'll get more practice. But this moves us fully into the second part of topic 3, which is derivatives of inverses. We actually only have 2 days on this, and the 2 days, the first day I would say is arguably less important. That's today. It's our inverse trig functions. The next day is going to be, I think, a little bit more important, though you could argue that each of them will almost certainly come up once on the AP exam. Now, you actually only have 3 formulas left to memorize in terms of derivative rules, right? Remember, if I tell you, what's the derivative of tangent of x, you say, oh, that's secant squared of x. And I'm like, yes, gold star for the day. You do have a couple more formulas. Just 3, though, I promise, just 3. So in order to, and part of today is going to be going through what some of those are, in order to be able to take the derivative of an inverse trig function, we first need to remember a few facts about inverse trig functions. It's one of those things that I think isn't covered super well in pre-calculus, and because we haven't done it in a while, you've probably forgotten a few things. So actually, I think the opener will probably take us the most time on this as a review. So I would suggest that you try to tackle this opener, inverse sine, inverse cosine, inverse tangent, on your own, but please use any resources you want. So use your cell phone to look it up. I think if you do your own research instead of listening to my soothing voice, you'll probably retain a little bit more. And do your best to answer each of these questions. For example, what are the domain and range for inverse sine? Given this equation, can you tell me what x is? Given the inverse or the arc sine of root 2 over 2, can you give me the value? Evaluate that expression. And then the same thing for inverse cosine and inverse tangent. We are not looking at inverse cosecant, inverse secant, and inverse cotangent, though we could. They're really just the same things as what we have down below, but I've never once seen the derivative of any of those come up, so I don't think it's really worth memorizing, and we don't need to overcomplicate what's already a pretty jam-packed course. So why don't you guys go ahead, pause this video, try the opener. Once you feel like you filled everything out, you can unpause and you can listen to me go through everything, not a bad review, or you can just skim it and move on to the actual calculus derivative part. All right, I think we are probably ready to go through these. In order to discuss the domain and range of the inverse sine function, when I mean the inverse sine function, I mean that we have an input, and I'll use the notation I don't like, but maybe we could do it like this too, arc sine, right? Either of these are acceptable. I like the arc sine so that we don't get that weird exponent that isn't an exponent involved. When I mean the inverse sine function, I mean that we have actually written the words inverse sine or arc sine in our equation. So this is not the inverse sine function. This, however, is the inverse sine function, and there are slight differences that we'll go into. But in order to know a little bit about the inverse sine function, then we probably should start with its inverse. So what is the inverse of inverse sine? Well, the inverse of inverse sine is sine. And actually, I'm going to write this a little bit differently. I'm going to say that, oh, what do we like to use? We usually use like, sometimes we use R. Let's use R. Let's use R for ratio. I think that's probably a good thing to do. And we're going to call it the ratio equals sine of theta. So if we wanted to talk about the inputs and outputs of this equation, right, and you probably don't need to write this, you can just listen, you should know this. The input for sine is, of course, theta, and theta is either a number of degrees or a number of radians. We use radians in calculus. Calculus is rad. And so if it's a number of radians or degrees, is there any limit on the radians that I'm allowed to substitute in here? And the answer is no. We can have negative radians. That moves us backwards around the unit circle. We can have positive radians. That moves you forwards around the unit circle. Or if you picture it as a graph and you have your theta axis, right? If you have negative radians, it's going to be something over here. Yeah, positive radians, something over here, right? Nothing terrible, but long story short, too late. You can use any radians you want. So our domain for this is, of course, all real numbers. You could use your fancy double bar R here, right? Either way, it means you're allowed to use anything you want for theta. The output, though, the ratio for sine, I'm using r for ratio, because usually when you rotate some amount, right, let's say we rotate up here and create a triangle, sine of this triangle is going to be the ratio of the opposite to the hypotenuse, right? We know that r is going to be the opposite of a triangle over the hypotenuse. It's always a ratio, and we need to remember that. So the output, though, because, and I shouldn't have erased that, the output of our triangle, since we're doing the opposite over the hypotenuse, and the hypotenuse is always the largest side of the triangle, the opposite's going to be smallest. Hypotenuse is the largest side of the triangle. So we're going to have a large value in the denominator and a small value in the numerator. Right? That gives us a fraction small over large, which always has to be less than 1. There is the one case where opposite and hypotenuse can be exactly the same, and that's when we end up at this pi over 2 rotation. And when they're the same, O divided by H, something divided by itself, you get 1, or negative 1 down here. So we say that the output, right, we say that our ratio is going to be an element or included between negative 1 to positive 1. Now, why did we spend all this time talking about how sine is set up? Well, we did that because we need to now talk about inverse sine. So imagine that you were given this same equation. Again, you don't need to write this, but r equals sine of theta. I should have given myself more room here. And someone says, hey, I would like you to undo sine, to basically isolate theta. Well, what do? Well, you would introduce the arc sine or inverse sine, or you would take the arc sine of each side of this equation. These cancel, and that leaves us with theta equals the arc sine of r. So when we're dealing with inverse sine, we need to realize that our input, our domain in this case, are the r values. Basically, they're ratios of sides. And our range, our output, is going to talk about theta. And theta is, of course, an angle. So for inverse sine, you're inputting a ratio of sides, and then you're getting an output of the degrees or the radians that created that ratio. And now, traditionally in inverse functions, we usually just switch the input and the output. And partially that is true. Our input here, our range, our input, our domain here is going to go from negative 1 to 1. We're only allowed to input values in the inverse sine that are between negative 1 and positive 1. Okay? However, our theta, our domain, is going to be slightly different. We're actually going to come back to that one in just a second, and we'll look at a couple examples here. So for example, if you were asked to find sine of x equals root 2 over 2, then we should note that this is theta because it's sine of theta, and this is a ratio of sides. Right? Input is theta, output is r. This is not an inverse sine function, it's a regular sine. You probably should know this. If you don't, though, positive root 2 over 2 is created by a triangle in the first quadrant because sine is the y-axis, right? And the y-axis is positive in the first quadrant, and it's also positive in the second quadrant. So we can make a similar triangle over here. And then to create a root 2 over 2 triangle, root 2, 2, root 2, and 2, and I know to place those there because we know that sine of theta is the opposite over hypotenuse. We need to recognize this as a special right triangle, and you might realize that you're multiplying by the square root of 2 to get over here. And so anytime you multiply by a square root of 2, that's got to be a 45, 45, 90 triangle. So maybe quickly redrawing this then, you would probably hopefully know that this is pi over 4, or 45 degrees. And then let's see, this is 2 pi over 4, so then 3 pi over 4 is going to give us the other rotation. So when it says given sine of theta equals blah, blah, then what is x equal? Well, we have a couple options. X can be equal to pi over 4, because that, when we substitute pi over 4 in here, gives us an answer of root 2 over 2. But x can also equal 3 pi over 4, because that's the same value. And in fact, you also might remember that with sine functions, you can do this an infinite number of times. You could get pi over 4 here, but if you go 2 pi further, full circle, you get there again. And another 2 pi, you get there again, and so on and so forth. And you could also do it backwards. You could spin negative 2 pi this way, right? Same idea. So How do we show that? Well, we just add on a nice 2 pi, and I usually use k here. Sometimes you see it with n, whatever sounds good to you. But either way, you add that on to show there's an infinite number of values that you can substitute in for theta to get this as an answer. But what about if this was written using our inverse notation, right? Imagine you took inverse sine of both sides here. Well, now I have inverse sine, which means my input is r. And my input here, now notice that I'm acting upon root 2 over 2. This is a function. It has to be a function. In this case, it's operating on root 2 over 2. And whenever you have a function operating on an input, then there can only be one answer. So the question becomes, what is the answer to the inverse sine of root 2 over 2? Well, if this is r, we know the answer, of course, has to be theta, has to be a number of radians or degrees that you rotate to create root 2 over 2. But aren't there a lot? Pi over 4 creates root 2 over 2. So does 3 pi over 4. So does negative 5 pi over 4. And so on and so forth. So which one do we pick? Oh no, there's so many choices. Well, this is where we get to our range restrictions for our inverse trig functions. So I'm just going to draw it quickly over here. If you don't have this, you can always find it on the internet. It's listed pretty much everywhere. We need to know that if this is pi over 2, this is negative pi over 2, and this is 0 radians, right? We can rotate positive pi over 2 or negative pi over 2, and I'm going to label this as pi. Pi over 2, here's pi over here. That our inverse sine function, so my inverse sine and my inverse tangent functions can either go to pi over 2 or they can go all the way down to negative pi over 2. And you'll notice by connecting that, that makes half a circle. Well, that's because in a half circle, we get all of the values that we need to find for our inverse functions. If you go any further than this half a circle, you just start to repeat yourself, right? We already said, again, this is my my ratio of sides in here. If I said, give me a ratio that's root 2 over 2, well, we could travel right here and create a triangle that's root 2 over 2. You could also travel further over here, but why bother creating another triangle? We got one that's already closer to 0. They picked this interval to be closer than 0. So what we do then is we say that the range here for inverse sine is going to be between negative pi over 2 to pi over 2. So that means if we're looking here and we're like, what rotation creates root 2 over 2? Well, it can't be 3 pi over 4. That's too far. That's past pi over 2. I think it's just got to be pi over 4, or 45 degrees if you're in degrees. Okay, so we should probably actually do tangent since we just talked about it. Tangent and sine have the same range restrictions. So let's remember a couple things about tangent. First, tangent, when you create a triangle, is created by looking at the opposite over the adjacent. And because these can be all sorts of different sizes, the adjacent can be infinitely small, the opposite infinitely large, my domain for regular tangent, right, tangent of some theta, which equals a ratio of sides, it equals the opposite over the adjacent. The domain for all of these is all real numbers, right? Nothing too bad. And then the range or the output is also all real numbers. Okay? So when we're looking at inverse tangent, my domain, which in this case, so if I rewrote this, we would say that theta is going to be equal to the inverse tangent of a ratio. The ratio in this case is allowed to be all real numbers. Something like that. Nothing too bad. However, my range is restricted. We already talked about that range restricted. You're only going to get rotations from negative pi over 2 to pi over 2. So given tangent of x equals negative 1, then what does x equal? I always forget this one, honestly. I don't know a lot about tangent. I almost always end up rewriting it as sine of x divided by cosine of x equals negative 1. That's an identity you should probably keep in hand. So really it becomes, in order to create 1, sine and cosine have to be the same value. Okay, and don't forget that this is going to be a theta in here if that helps you think about it. So where are sine and cosine exactly the same? Well, they're exactly the same with 45, 45, 90 triangles, x, x, x root 2. This ratio and this ratio give you the exact same answer. Of course, to get -1, they have to be opposites. So I think that occurs in quadrant 2, right? Cosine's negative. So that's going to be, I think x can be 3 pi over 4. Right, that brings us here. I don't think 5 pi over 4 is going to work because they're both negative. So when you get a negative divided by a negative, it'd be +1. So I think, excuse me, sorry. I think the last triangle will be, look at this, positive x, negative x. It looks like 7 pi over 4. But what we might notice here is that we have one triangle here and a second one here. So we rotate here, and then we go 180 degrees, then 180, and then 180. So tangent's actually that weird one where you can say plus just pi k. Tangent always repeats itself every pi instead of every 2 pi. Now, what if we asked for the inverse tangent of -1? Well, the inverse tangent of -1, again, this is my ratio of sides. My ratio of sides, something like this. We know it's the same question as before, but we have our range restriction. We can only give one answer. So which triangle is it? Well, looking back at our range restriction, we know it has to be this triangle down here, right? It can only be in the first or fourth quadrants. And it has to be between -pi/2 to pi/2. So the question you ask yourself is, what's the fastest way to get to this quadrant? Well, it's not traveling around and going 7 pi/4. In fact, it's going backwards and just going to -pi/4. And then we get to our last one. Inverse cosine, we again should know, but you might have forgotten, that inverse cosine goes from 0 to pi. Right, this is my range restriction for inverse cosine. I guess I could say x, but a ratio is probably a better way to put it. And that's because cosine is the same value in the first and the fourth, because cosine is the x-axis, and the x-axis is positive there. So we need one part where cosine is positive, one part where it's negative, and the closest to 0 that we stay positive with is 0 to pi. So there is my restriction, moving through hopefully a little quicker. Again, this could be a full review for you guys, but it might not. I'm not sure. Treating inverse cosine as theta equals the inverse cosine of some ratio. Regular cosine has a domain, right? Regular cosine inputs angles of theta. So the range we just talked about for theta then has to be from 0 to pi. And then my domain here, well, the domain's going to be just like sine. Regular cosine, the output is -1 to 1, so the input for inverse cosine has to be from -1 to 1. Given cosine of x equals 1/2, then what does x equal? I always have to draw a triangle on these guys. I really don't have them memorized. Should you memorize your unit circle? Sure, you're probably going to get answers faster. How often do specific trig values come up? A little bit. Usually they're really basic ones like quadrantal angles like cosine of pi or something, but you might get one problem that asks about this, and you do want to be efficient at it. So we know cosine's positive here, and we also know cosine is positive here because cosine is the x. If it's going to be 1/2, right, we can maybe see that we're multiplying by 2 here. Whenever you multiply by 2, you should know that's a 30, 60, 90 triangle, right? 30, 60, 90 triangles, it can either be x, x root 3, and 2x, and I think that's what this one is because we multiply by 2, and x is the smallest side. You can think of it as times the square root of 1, definitely smaller than the square root of 3, so it's opposite the smallest angle, which makes this one 60 degrees inside here. So 60 degrees, and then if I wanted to rotate all the way around, well, instead of 60 degrees, we might remember that's pi over 3, so I think this is 3 pi over 3, 4, this has got to be 5 pi over 3. So I think x can be two values here. X can either be 5 pi over 3, and then repeat every 2 pi k values, or x can be pi over 3 and repeat every 2 pi k values. Again, this is probably more than you'll need for this year, but an extra refresher is not a bad thing since many of you are still struggling with those trig values. Learn your trig values. All right, inverse cosine of 1/2. Well, we have a lot of answers, but we need to remember that our cosine can only be in the first or second quadrant from 0 to pi. Luckily, we already have that. First quadrant, pi over 3 is between 0 and pi, so we get pi over 3. Awesome. Now, we did absolutely no calculus there. So let's get into the calculus part. It's actually much easier than everything we've done, and you, I think, will like these inverse trig derivatives. They're very surprising. at least to me. So to take the derivative of inverse sine, we're going to begin with what we know. Y equals sine of x. Now don't forget that the first step to find any inverse is you switch the input and the output. Right? It's probably what you learned in algebra 2. To find inverses, you swap those, so we get x equals sine of y. And technically, we're done. That is the inverse function, right? Because the input has become the output. Now, typically, usually what happens is once you find this inverse, they usually have you solve for y. But we're not going to solve for y here. We're just going to remember that relationship, right? This is another way to write inverse sine, just a little bit more succinctly without having to use that weird notation. Okay. Now, let's just go ahead and take the derivative of this. So we're going to take the derivative of x and take the derivative of sine of y. And it's a good thing we just practiced our implicit differentiation. We're going to crush it. The derivative of x with respect to x, that's dx is 1, right? Cancels. The derivative of sine of y, chain rules in effect here, becomes the cosine, but keep y the same. And then now we're going to multiply by the derivative of the inside. This d dx, though, means it's going to be dy dx. And then I think isolating dy dx, because our whole goal here is to isolate dy dx, all we need to do then is divide cosine of y over to the other side. So we get 1 divided by cosine of y equals dy dx, or I wrote it over here as y prime. And great, we've found the derivative of inverse sine. However, this derivative uses an input of y, and although there's nothing wrong with that, traditionally we like our derivative to be in terms of just x if we can. Sometimes we use x and y, but it's very unusual to see something with just y. And we can do that. So what we're going to do is remember one identity that I think most people do remember from pre-calculus or trig, and that's our Pythagorean identity. In particular, sine squared of y plus cosine squared of y is 1. And use any variable you want. I used y here because we're using y up here. It should make a decent amount of sense. Let's go ahead and isolate cosine of y. Right? Now, when you isolate cosine of y, eventually you're going to have to take a square root, do that last, and you're technically going to get a plus minus in your answer. But remember that we're finding the derivative of inverse sine, which is restricted between negative pi over 2 and pi over 2. Right? Inverse sine is what we started with, and reminding you that negative pi over 2 to pi over 2 spans this distance. Right? And if you think about the x, which is cosine here, that's always positive. So since the cosine of any of those values is positive, there's really no point. In fact, it's wrong to put plus minus. There's only going to be positive answers here. So let's work on isolating that. So to isolate cosine, we're going to first, I think, probably subtract sine squared from both sides. So cosine squared of y equals 1 minus sine squared of y. And then to finish isolating cosine squared, we take the square root. 1 minus sine squared of y. Cool. All right. Well, then that means that instead of writing the beautiful derivative of 1 divided by cosine of y, we could write the beautiful, well, this is actually really not beautiful, is it? 1 minus sine squared of y. Now, that's gross, and it didn't help us. I think the whole point is we want to rewrite this so it uses x instead of y, and I think I just made it more complicated. So why would we do that? Well, don't forget, we know something about sine of y. In particular, didn't we learn up here that x is equal to the sine of y? So why don't we go ahead then and replace sine of y, and please don't forget that sine squared of y really means sine of y squared. So I'm going to replace sine of y, don't forget my square, with x. And look at that. That is pretty darn awesome, because now we know, at least to summarize, we'll do this on our next page, that if you have the inverse function for sine, the inverse sine, that the derivative is 1 divided by the square root of 1 minus x squared. You're like, well, why are you so excited? Well, you should be excited. Look at this derivative. We started with a trig function, right? We started with y equals inverse sine of x, which may terrify you. You're like, I don't get trig functions, and inverses are even worse. And then we took the derivative. the derivative has no trig function in it, and that is awesome. I think it's really, really fascinating we can do that. It really sits in the same league as the derivative of natural log, right? That was that strange one where it becomes 1 over x. It's like, whoa, we had a transcendental function, now it's gone. Same thing, we had a trig function, now it's gone. Well, let's try a couple practice problems. So I have A and B here. Please go ahead, try them on your own. You should be okay with them. And then once you're done, unpause and we'll see how we can do. All right, so running through this quickly, inverse sine of 2x. Well, the inverse sine of whatever x is, we know is going to be 1 over the square root of 1 minus whatever the thing is inside squared. Think of this as a u substitution, a chain rule if you want, but what I've done here is the derivative of inverse sine. I haven't even touched the 2x yet. We can't take the derivative of 2x in here because this is just the derivative of inverse sine. 2x is just tagging along, biding its time until it's its turn. Well, now that we've done the derivative of inverse sine, now we can multiply chain rule by the derivative of the inside, which is 2. And so maybe cleaning this up a little bit, move the 2 on top of the fraction, 1 minus 4x squared, and that's about as far as we need to go. So don't forget that chain rule. It never goes away. It's always there. Just waiting to strike. All right, tangent line here. We know our tangent line is going to be y prime of, what's my x value? Of 1/2 times x minus 1/2 plus y of 1/2. All right, we should probably find these things. We know that y is the inverse sine of x, and so when I want to find y of 1/2, it really means do the inverse sine of 1/2, and I'm going to cheat a little bit. I know in the opener we found inverse cosine of 1/2 is pi over 3, so I know then that inverse sine of 1/2 is going to be the other one. That's going to be pi over 6. Right? They complement each other. It's cosine, complementary sine. So that one's pretty easy. Then we need to go through, and maybe I should color code. We just took care of that piece. Now we need to go through and do the actual calculus part. So in order to find y prime of 1/2, we need to find y prime of x first. The derivative of inverse sine, 1 divided by the square root of 1 minus x squared. So when I find y prime of 1/2, we get 1 minus the square root of 1 minus 1/2 squared. We can simplify this a little bit. It's an ugly slope, and we could use the ugly slope. Let's do a little practice here. We know that 1/2 times itself, half of a half is a quarter. And we know that 1 minus a quarter is going to be 3/4. All right, and then we also know that we're allowed to distribute a square root if we have division or multiplication. So I'm getting square root of 3 divided by 2. And we lastly know that 1 over a fraction is just the reciprocal of that fraction, 2 divided by the square root of 3. And sure, you could rationalize, but I don't want to, and you can't make me because this is a video. So finishing this off then, we can see that our slope is the fairly lovely 2 divided by square root of 3. And then we have x minus 1/2, and we found that y of 1/2 is pi over 6. And we've got a crazy looking tangent line with square roots and pi's in it, but this is a line, and that is our tangent line to inverse sine. Now, before you start freaking out, I'm like, wow, that is a lot of work. And before I freak you out even more, when we remind you that there are 6 inverse functions, we get some good news. Inverse trig derivatives rarely come up. However, there is usually one problem on them each year. Sometimes it's from the first semester and they ask you to take the derivative. More commonly, it's been from the second semester where you have to go backwards, and that's pretty tricky, right? If they gave you something like this and said, I want you to find the function that you took the derivative of to get here, one of your last guesses would be a trig function. Why would that be a trig function? Well, it is, and we'll talk more about it next semester. But yeah, definitely a little trickier to work backwards, and that's why I think that those come up second semester more often. Now, there are 6 derivatives here, right? We talked about one of them. The derivative of sine is right here. 6, obviously. I am just going to ask you to memorize 2 of them, inverse sine and inverse tangent. Why those 2? Because those are the only 2 I've ever seen show up. Now, Are you going to use all of them today? Of course you are. You're going to practice inverse secant, inverse cosecant. Notice also that it's really, really nice because these derivatives are exactly the same as their counterparts, just with a negative out front, right? They're identical. Just put a negative out front and you have it. The inverse secant and cosecant look wild with those absolute values, but we're not going to get into the proofs for any of those, so don't stress it. Okay. Now, I'm only going to test you on the two that I highlighted. If the others come up on the AP exam, you do need to know them. However, I'm only going to test you on two, so if you have the time, memorize them all. If you don't, though, and you want to narrow it down, you can just memorize these two. Remember, at the beginning of the lesson, I said you only had 3 more derivatives to memorize. Here are the 2 for today. That means that there's going to be 1 more derivative formula you need to memorize. That will be tomorrow. Okay. Now let's actually take a quick look at each of these. I wrote all of these derivatives, instead of x, I wrote them with f, where f stands in for a function, right? So this way we can really see the chain rule. When you do the inverse sine, the derivative of inverse sine of a function, it's 1 minus that function squared times the derivative of the function. Right? Now, sometimes I see people do weird things. They're like, oh, then that means when I do the inverse sine of x, and you say, hey, take the derivative of this, then that's going to be 1 divided by 1 minus x squared times x prime. No, don't write x prime. It literally means the derivative of x. The derivative of x is 1. Right? Not x prime. The derivative of x is 1. So make sure you keep that straight. The other one that, of course, I wanted to mention was the derivative of inverse tangent. It is a little bit even nicer than inverse sine. It's 1 divided by 1 plus whatever was inside squared. And I like to write them both this way. Sometimes you'll see inverse tangent as the function squared plus 1. I like it this way, so you can just see 1's positive, 1's negative. Square root has a negative, no square root has a positive. Okay. Now let's go ahead and do a couple practice problems here. Again, I'm going to have you guys try it out, and then I will go through it with you. The only other thing you have to do today are a couple practice problems at the end. I have all of these practice problems worked out in my worked out solutions on Teams. So if you need extra help, you can email me, but I think you'll be okay. So let's finish off with these two today. So pause me quickly, try A and B, unpause, and we'll go from there. All right, hopefully you were able to get through these two. I think B is pretty tricky, might have stumped a couple of you. A is a little bit more straightforward, especially because we just did one. If you can't write tangent lines yet, you really need to come ask for help because we do this a lot. So we're going to do f prime of 1 times x minus 1 plus f of 1. Color-coded this time, winning. So let's start with f of x. We know f of x is the inverse tangent function, and they're asking us to find f of 1, which is the inverse tangent of 1. Again, cheating a little bit. We did something similar to this on the opener where we talked about the inverse tangent of negative 1, right? And those were these two right here. So the inverse tangent of positive 1 is going to be these two, positive 1, first quadrant. Sine and cosine are the same at pi over 4, right? Sine and cosine of pi over 4, when you divide them, gives you an answer of 1. All right, then we need f prime. So the first thing we'll need is f prime of x. The derivative of arctangent inverse tangent is 1 over 1 plus what was inside squared, x was inside, right, squared, times the derivative of what was inside. The derivative of x is 1. So did I need to write the 1? No, of course not, but sometimes that's helpful. So f prime of 1 then is just going to become 1 over 1 plus 1 squared. We're not going to multiply by the derivative of 1. It doesn't become times 0. We already did the chain rule over here. We're not doing the chain rule when we evaluate. There's no calculus going on here. We're just plugging in a number. So don't overthink it. It becomes 1/2. Finishing off our tangent line, we have a very nice slope of 1/2, x minus 1, and then plus pi over 4. Okay. And there's our tangent line. All right, part B. What is this limit monstrosity? Why has it come up to mess with my life? Well, this limit is actually the definition of a derivative. It's one of the two that you need to know and recognize. In particular, it's the limit as h approaches 0, f of x plus h minus f of x over h. And this defines the derivative of the function. And of course, if they replace that x with a value, and in this case they did, they say a is a value, right? F of a plus h minus f of a divided by h, then that's finding the derivative of the function at a. So there are three steps here then. We are first going to identify what is, I'll write this down here, what is f of x? Well, looking at this, hopefully we can see that if these were x's in here, that f of x is going to be the inverse sine of x. So first step is we know that f of x is the inverse sine of x. Okay, second step, we're going to find f prime of x. Okay, well, we know that f prime of x is the derivative of inverse sine, which is 1 divided by the square root of 1 minus x squared times 1, but we don't really need that. And then last step, we need to figure out what is f prime of a. Well, in this case, f prime of a is 1 divided by the square root of 1 minus a squared. Now, what did I do here? Well, I just worked through this left side. I ignored the equals to. This left side, if you evaluate it at all, evaluates to this. So let's go ahead and rewrite this problem, but instead of the left side, let's rewrite it as what's 1 divided by the square root of 1 minus a squared. Don't forget, though, that there's still a right side. Now we have an equation that we can solve. Our goal is to find the value of a. We have an equation. We have a. Let's solve. So you might want to, again, pause this here because I'm going to give you a separate way to solve for a that you might not have thought of before. And I don't want to, warp your mind early on. So I'd rather you try this first. And then once you've done it, unpause and I'll talk about my method. Okay, my method really has to do with where this a is located. I don't like solving when a is in the denominator. So one of my first steps, instead of doing something to both sides, or I guess moving something to the other side, is I actually first flip these over. Now, technically, when you flip a fraction over, you raise it to the negative first power, right? You're allowed to do a power to each side. There's nothing wrong with that. That keeps with our rules of algebra. But I usually just think to myself, just flip both fractions over. And you're like, well, wait, 2's not a fraction? Of course it's a fraction. It's 2 over 1. So when we flip these fractions over, it becomes the square root of 1 minus a squared over 1. And the other side becomes 1/2. We don't even need the over 1. And now we have a much nicer problem to solve. How do we undo the square root? We square both sides. So 1 minus a squared. I'll show you this, right? Square both sides. 1/2 times 1/2 is 1/4. And then I'm going to add a squared to the right side and subtract 1/4 to the left side. Kind of 2 steps in one. 1 minus 1/4, well, that I think is 3/4. And then we need to take the square root of that. When we take the square root, you could put plus minus. However, well, we don't need to go into it. So if you want to put plus minus, that's fine. So take the square root of both sides. We end up with 3/4 equals a. And if you wanted to distribute the square root, we get square root of 3 over 2 is a. So what did we actually find here? Well, that tells us if we wanted to know the derivative of inverse sine at root 3 over 2, then the answer is 2. Yeah, so it's a pretty gnarly problem, but I think it's a fun one, gets you some algebra practice. The rest of these are much more straightforward, I promise. There are a couple definitions of the derivative, but nothing nearly as complicated as you just saw. Try these 6, and then once you're done, check your work with my solutions, and be ready to come back tomorrow to talk about generalized inverse functions. So we're almost done with all our derivative rules. Thanks for sticking through.